Computer processing refers to the analysis and mathematical calculations that a computer system performs on a piece of input or data in order to produce a result. This entails moving electrical signals from one part of the computer system to another. So the collection of devices responsible for fulfilling these tasks is our processing devices. Every computer system has a CPU and a main memory in its processing system. Let's take a closer look at each of these devices. First, let's talk about CPU. The CPU, or Central Processing Unit, or for short the processor, is sometimes referred to as the brain of the computer. Its main job is to fetch instructions, perform the actions defined in the instructions, and produce an output. Internally, the CPU has two other devices, the control unit and the arithmetic logic unit. The control unit, or CU for short, is the coordinator. It communicates with other components in the computing system to coordinate their activities. It is also responsible for determining the next instruction, from where to get that instruction, and for transmitting that instruction to other components through the transmission of electrical signals. The arithmetic logic unit, or the ALU for short, is responsible for performing mathematical calculations and the calculations needed to transform data from electrical signals to meaningful characters that we can understand. This is necessary because, as you will see soon, a computer stores its information in binary digits, or zeros and ones. So for information stored in a computer to make sense to us, we need a way to convert those zeros and ones to alphanumeric characters we can read and understand. The ALU is responsible for doing those conversions. Popular CPU manufacturers are Intel, AMD, and Qualcomm. When buying a computer, the CPU or processor is a major factor to consider because it is part of what makes your computer fast. Usually, if you're buying a desktop or a laptop, you can choose between Intel or AMD CPUs. Each CPU manufacturer has a classification for their CPUs. You can learn more about Intel's processor classifications at this URL. And you can learn more about AMD's processor classifications at this URL. These classifications will tell you how fast a given CPU is and how well it performs in different situations. The main memory is the second device in the processing system of a computer. It is a random access memory, or RAM, that holds the information with which the computer is currently working. It is called a RAM because the information stored on it can be accessed in any order. It is a very volatile system, meaning it will lose all of its information as soon as you turn your computer off. Because of its volatility, you can think of it like your short-term memory. The main memory and the CPU have a relationship in that together, they determine the speed of your computer. The main memory has a size that can be measured in bytes. But before we talk about the main memory size, I want us to take a detour and talk about how the main memory stores information. And make sure to pay extra attention to this lecture because it comes up repeatedly, especially when we start writing code. Keep in mind that regardless of the fancy terms we use in this course, electronic computers are simply a system of electrical devices. So every component in them operates with electrical signals. The main memory is no exception. It's pretty much a circuit board with a bunch of electrical switches on it. Think of the circuit board as this blank space. Now, think of each of these circles as a switch on the circuit board. Each switch is called a bit, or binary digit. A bit is the most basic unit of data or information. Just like the switches on your wall at home, a bit can be turned off or on. The off and on positions of a bit is known as the state of a bit. And that state, represented mathematically as 0 for off and 1 for on, defines the computer's binary language. The binary language is a language with only two characters, 0 and 1. When a bit is off, we say its state is 0, and when a bit is on, we say its state is 1. A bit can ever only be in one of these two states, never both. The bits are further organized on the circuit board in groups of 8, called a byte. Each byte has a unique number, known as its address. A byte's address serves the same purpose as your home address, and it is ordered from lowest to highest. When the main memory stores information, it arranges the states of the bits at a given address in a pattern that represents that information. For example, Consider the following main memory. Currently, it is empty. As a result, all the bits are off. If we wanted to store the number 25 at address 8, we will have to arrange the states of the bits at that address to represent the number 25. To do that, we first must convert 25, which is currently a decimal number, or in base 10, our method of counting, to a binary number, base 2, zeros and ones, the computer's language. When you do that conversion, you will see that 25 in base 10 is equivalent to 11001 in base 2. Now that you have your binary value, you can immediately see that each one in that value represents a switch or bit at address 8 that is on, and each 0 represents a switch or bit at address 8 that is off. So, starting from the rightmost switch at the location, we always start from the right when dealing with binary numbers, we can store our value as follows. At this point, you might be thinking, if a computer can store the decimal number 25 by converting it to the binary number 11001, and then use that number as a state of bits, how will the computer store a letter or an image? Well, it turns out the computer uses the same mechanism for storing not just letters or images, but everything else as well. So far, we have shown how the computer stores a decimal number, like 25, in its memory. With that simple knowledge, we can show that a computer can store pretty much anything. All we must do is figure out a way to assign a number to any character. Luckily for us, a group of really smart people came together a long time ago and came up with something called ASCII, or the American Standard Code for Information Interchange. ASCII is a standard which assigns a decimal number to a given character. For example, the capital letter A is assigned the decimal number 65. The capital letter B is assigned the decimal number 66, and so forth. Here is an example of an ASCII table. Let's go through it. As you can see, each character has a decimal number assigned to it. There are some characters that are invisible. Those are characters that do not have any visible representation on the screen. Example would be the tab key. You can use this character by pressing the tab key on your keyboard. When we scroll down here, you can see that these characters are visible. For example, you can see the uppercase and lowercase alphabets here. The original ASCII standard only included 128 characters, as you can see in this table. Obviously, that doesn't account for all the characters in all the spoken languages in the world. So, a second version of that standard, extended ASCII, includes an additional 128 characters to give us a total of 256 characters. The standard includes letters with accent from languages like French. So, if we wanted to store the letter A, we just find its decimal number 65 on the ASCII table, convert that to binary digits, and store those bits in memory. So we take A, which will give us 65, and then 65 will give us this binary number. A collection of characters in each character standard is called the character set of that standard. Every character set has a maximum number of bits or bytes needed to store its characters. For example, as you might have noticed, we only need exactly 8 bits or 1 byte to store the largest character on the extended ASCII table. This means the ASCII standard is an 8-bit character set. To show you what that means, let's take another look at the extended ASCII table. As you can see, the largest character on this table is the Latin small letter y with diaresis, and it has the decimal value 255. If we put that decimal value in our programmer calculator, we get the binary value 11111111. If we arrange our bits at any memory location, we can see the value fills the entire byte. When all the switches are on at a memory location, we say the location is full. Because all the ASCII standards only account for 256 characters, it's obvious that they do not account for most spoken languages. As a result, the Unicode character standard was created. The Unicode standard is a superset of the ASCII standard, meaning all the characters found in ASCII can be found in Unicode, plus a bunch more. The Unicode character set has characters that require up to 32 bits or 4 bytes. The emojis we love so much are also defined in the Unicode character set, and new ones are being added. New emojis are being added frequently. For example, the smiley emoji has the decimal value 403699114, which is equivalent to the following bits. That's a lot of bits. As you can see, we need up to 32 bits to represent our beloved smiling face with smiling eyes emoji. There is no way we could store emojis with the ASCII standard. We needed a Unicode character set to welcome our picturesque friends. At this point, you can see how the computer stores words and sentences. What about images or videos? Well, it turns out when you zoom deep into an image, like this one, you can see that it is made up of tiny squares. Each square is called a pixel. A pixel is simply a speck of color on your screen. Colors on a computer screen can be simplified into the mixture of 3 color channels: red, green, and blue. We can represent any color by specifying the quantity of red, green, or blue in it. The quantity of red, green, or blue in each color can go from 0 to 255. So for the color white, the red channel is 255, the green channel is 255, and the blue channel is 255. For the color black, the red channel is 0, the green channel is 0, and the blue channel is 0. So if we took a single pixel from this image, we can calculate its channel values. Those values can then be converted to binary, and they can then be stored in the computer memory. Wow, that's a lot of work. Well, what about videos? If you think about it, a video is just a bunch of sequential images stitched together. Each image is called a frame. A video appears to move because a bunch of sequential frames is shown per second. In fact, you might hear something like a video is playing at 24 frames per second, which indicates that in the given video, there are 24 frames or images showing per second. So to store a video, simply break it down to its individual images and collect all the pixel values and convert them into decimal numbers. Convert those decimal numbers into binary, and then voila, you can store the binary numbers in the respective memory locations. As you can imagine, if you had to do all that work yourself whenever you visited YouTube, you probably will never watch videos in your entire life. Lucky for us, the computer employs a concept known as abstraction to do all this work for us behind the scenes. Abstraction allows the computer to hide all the detail of converting frames to images and images to pixels and pixels to decimal numbers and decimal numbers to binary numbers from you, and simply present you an interface where you can click a single button to play your videos. By the way, abstraction is all around us, not only in computer science. It is, for instance, the reason you can learn to drive a car without worrying about how a car works internally. It is also the reason that when you learn to drive one car, you can pretty much drive any other car in the same category. If you had to think about what happens in a car's engine every time you press the gas, you probably would never drive. So abstraction is a very important concept, not only in computer science, but in all our lives. Okay, now let's get back to the size of the computer memory. Now that you know how a computer stores information, let's get back to the memory's size discussion we promised you earlier. While the basic unit of data is a bit, the main memory is usually measured in gigabytes. The following table shows the conversion factors between memory sizes. When you buy a computer, depending on your industry, the larger the memory, the better. For example, if you do a lot of video editing in software like Photoshop, you will need a computer with a lot of memory because Photoshop uses a lot of memory. When you notice your computer slowing down or freezing, you are most likely running low on main memory or CPU usage. Most modern computers come with 8 gigabytes of main memory. In most cases, that is plenty.